Welcome back, everyone. We're diving into a topic today that might seem a bit intimidating at first, tensors. Those multidimensional arrays that make some folks break out in the cold sweat. But don't worry, we're here to demystify them. We've got some great excerpts from a data science textbook that really focus on how tensors can help us unlock hidden patterns in complex data, especially when it comes to feature selection and extraction. Ready to unravel the mysteries?
Absolutely. It's an area ripe with potential, and the excerpts you've chosen really highlight a core challenge in data science, making sense of all that data and figuring out which features are truly meaningful.
Right. It's easy to get lost in the sea of data. So, to make sure we're all on the same page, the source material starts with a nice little refresher on vectors and matrices, laying the groundwork before things get really wild.
Exactly. And I appreciate how they link those concepts to geometry. Visualizing data in multiple dimensions is so key, and matrices give us the framework. Remember that example about groceries from the text? Think about how you could represent the prices and weights of your weekly shop at different stores as vectors. Combine all those, and boom, you've got yourself a matrix.
Right, like each grocery trip is a point on a graph, but each point holds all that extra information. But then hold on to your hats, we take the leap from matrices to tensors. Even the source material mentioned that people can get a little hesitant here. Tensors seem like these mysterious multidimensional beings.
It's true, they can seem a bit intimidating. See, unlike matrices, which have that straightforward geometric representation, tensors can have multiple unfoldings, which makes them trickier to wrap our heads around. Imagine trying to flatten a 3D object onto a 2D surface. It gets messy. But the excerpts do a good job of using concrete examples to guide us.
That's what we're here for. Okay, so we've encountered these so-called tensor titans, but how do we actually wrangle them? The text dives into three main methods: CP decomposition, Tucker decomposition, and tensor train decomposition.
Each one offers a different way to represent a complex tensor as a combination of simpler components. It's like, you know how you can break down a complex flavor into its individual components? Each decomposition method gives you a different perspective on those components.
Okay, now that's an analogy I can get behind. I love thinking about food. So tell me more about these different flavors of tensor decomposition. When would you use one over the other?
Well, let's take CP decomposition. It's described as potentially revealing those aha moments because it focuses on making the components interpretable. But, and there's always a but, it can be computationally expensive.
So powerful but potentially time-consuming.
Yeah.
Why is that? What makes it so computationally hungry?
Think of it like this. You're trying to recreate a complex flavor, but only using a handful of spices. It might take a lot of trial and error to find the exact combination that works, lots of calculations going on behind the scenes. But once you do, you know precisely what creates that unique taste, the aha. And you understand how each spice contributes. That's the interpretability.
That makes sense. So what about the other methods? How do they compare? What are their strengths?
Well, Tucker decomposition is often a more predictable path, as the source material points out. Think of it like breaking down the flavor into those basic taste categories: sweet, sour, salty, etc. You get a good general understanding, even if it's not as immediately insightful as CP decomposition.
Okay, broader strokes, but maybe a quicker analysis. And then there's tensor train decomposition, right? Finding the most efficient representation of our data.
You got it. This method is all about finding a good balance. We want a representation that is accurate but also manageable. It's like finding the shortest, most elegant recipe to recreate that complex flavor.
I like that. Efficiency is key. But we've got all these different ways to break down tensors. How does this actually help us in practical terms? This is where things get really fascinating for me because we can use these techniques for unsupervised feature extraction.
You're getting to the heart of it. Imagine you've got this massive data set, tons of features, but you don't know which ones are the key players.
Right. It's like trying to find a needle in a haystack. But instead of a needle, it's, well, valuable insight. I might need to work on my analogies a bit.
I think it works. But the point is, how do we find those valuable insights? Think of tensor decomposition as this powerful lens. By decomposing the tensor representation of your data, we can zero in on the most influential features.
So it's like those mathematical scouts sifting through the data and saying, hey, this is important, pay attention to this.
Exactly. And this is especially powerful for unsupervised learning, right? Where we don't have labeled data to guide us. We're relying on the data itself to spill the beans.
This is already blowing my mind, and we're just getting started.
Oh, we've only just scratched the surface. Now let's see how these decompositions are used in the real world. The source material gives some pretty interesting examples.
Like using tensor decomposition to identify correlated features. That one really jumped out at me.
It's a great one. Imagine we're looking at customer purchase data. We want to understand which products tend to be bought together, those people who bought this also bought that insights.
Okay, so instead of just looking at what people buy individually, we're looking for those hidden relationships between purchases. Like maybe people who buy a certain type of cheese are also likely to buy a particular type of wine.
Exactly. Even if those two products seem totally unrelated on the surface.
Hmm.
Exactly. That's the power of it, right? Uncovering those unexpected connections. And think about the implications. We're talking about product placement, targeted marketing, even inventory management.
It's like those online recommendations, but on steroids.
Hmm.
Like customers who bought this obscure vintage record also bought this antique teacup. Okay, maybe not exactly like that, but you get the idea.
You got it. It's about finding those hidden affinities. And it's not just about shopping carts either. The source material talks about how you can apply this to all sorts of fields, understanding correlations in financial data, uncovering patterns in medical images. The possibilities are pretty much endless.
Endless possibilities. I love it. But let's get practical for a second. If our listener is thinking, this is amazing, but how do I actually use it? What are some tools they can explore? We're talking custom-built algorithms, or are there ready-made solutions?
Good news. There's a whole ecosystem of tools out there designed specifically for working with tensors. In fact, the source material even mentions a few in its appendix.
Oh, nice. Always appreciate a good appendix. So what are we talking about? What should our listeners check out?
Well, if Python is your jam, TensorFlow is a great place to start. Specifically, their T3F and tensor libraries. They provide the functions you need to actually perform these decompositions and dive into the analysis.
TensorFlow. That's a big name. Even I've heard of that. It's like the go-to for a lot of machine learning folks, right?
Absolutely. It's become really popular, especially for deep learning. And these specific libraries within TensorFlow, they're like your specialized toolkit for working with these multidimensional structures.
Got it. So if you're ready to get your hands dirty with tensors, TensorFlow is the place to be. What about our users? Anything for them?
The source material mentions a few CRAN packages for R, things like tensor and ntensor, and even one specifically for applying tensor decomposition to single-cell RNA sequencing data, which is pretty cool.
Wow, so niche. There really is a tool for everything. Okay, but before our listeners go off and build their tensor empires, we talked about breaking these things down, but the source material also emphasizes interpreting the results. What are some key things to keep in mind there?
Great question. Doing the decomposition is just the first step, right? The real magic happens when you interpret those results, and that's where statistical analysis comes in. Those singular value vectors we get from the decomposition, they hold valuable information.
Right, like each vector is a clue, and we're trying to piece together the bigger picture.
Exactly. The source material gives an example of using principal component analysis, or PCA, to understand these components. Let's say you're analyzing images of handwritten digits. PCA can help you identify the principal components, the things that really define a 7 versus a 3.
So we're not just looking at each pixel in isolation, we're finding the underlying patterns.
Exactly. Those principal components might be things like the curvature of a loop or the thickness of a line. It gives you a much deeper understanding than just looking at pixels in isolation.
That's amazing. It's like PCA helps us see the forest for the trees, even within something as complex as handwriting. But with all this analysis, how do we know what's really meaningful and what might just be random noise in the data?
That's where statistical significance comes in. The source material talks about using p-values, like a nonsense filter. If a component doesn't meet a certain threshold, it's probably not worth your attention.
So even though tensors give us all this power, we still need to be careful not to overinterpret the results.
100%. Like any powerful tool, you need to use it thoughtfully.
Speaking of limitations, the source material doesn't shy away from those either, does it?
Not at all. It's very upfront about the fact that interpreting the results, especially for higher order tensors, can be really challenging. And that difficulty is probably a big reason why tensors aren't even more widely used.
So it's a trade-off. The potential is huge, but there's a learning curve.
That's a great way to put it. We need to be smart about when tensors are the right tool and when other techniques might be a better fit.
Right, like you wouldn't use a hammer to tighten a screw.
Yeah.
Sometimes you need a more specialized tool. And speaking of specialized, you were particularly interested in feature selection and extraction. Chapter 5 of your source material, TD-based unsupervised feature extraction, dives right into that.
Yeah, Chapter 5 really gets into the nitty-gritty, using tensor decomposition for unsupervised feature extraction, especially when we're dealing with situations where we don't have labeled data to guide us. It's like letting the data reveal its secrets on its own terms, right? Exactly. It's like those choose-your-own-adventure books. The data presents us with a problem, and we get to choose which tensor decomposition method will lead us to the most insightful solution.
I love that analogy. And just like those books, the source material points out that the specific type of tensor decomposition we use can significantly impact the results and how easily we can interpret them.
Absolutely. Each method has its own strengths and weaknesses. The source material highlights how Tucker decomposition can be a bit faster, computationally, less demanding, but sometimes understanding the meaning behind those components might take a bit more effort compared to, say, CP decomposition. It's a balancing act.
A balancing act between speed and interpretability. It's like choosing between different paths through a forest. Some might be quicker, while others might offer more scenic views, but ultimately they can all lead you to some pretty amazing discoveries.
I like that. And speaking of navigating complexity, the source material emphasizes that statistical analysis is crucial for validating the features we extract. We don't want to be led astray by random noise.
Right, we're trying to find gold, not fool's gold.
Exactly. The text specifically mentions statistical tests, like the chi-squared test. It's about ensuring the features we're focusing on are actually meaningful and not just random fluctuations in the data.
It's a good reminder that even with these advanced techniques, a healthy dose of skepticism and rigorous analysis is always necessary in data science.
Couldn't agree more. It's all about combining these powerful tools with a critical and discerning mind, and your excerpts do a fantastic job of highlighting that.
This deep dive has been amazing. We've covered so much ground, from the foundations of vectors and matrices to the incredible potential of tensor decomposition for uncovering hidden patterns in data.
And this is really just the tip of the iceberg. The field of tensor analysis is constantly evolving, with new and exciting applications being discovered all the time.
So for our listeners who are feeling inspired to continue this journey, where should they go? What resources would you recommend?
Well, the textbook excerpts you shared are an excellent starting point. But beyond that, there's a wealth of information available online. A simple search for tensor decomposition in data science will lead you to a treasure trove of resources. And for those who really want to dive into the cutting edge, exploring academic journals and papers, particularly those mentioned in Appendix B of your source material, can open up even more avenues for learning and exploration.
We'll be sure to include links to those resources in the show notes. Well, that wraps up our deep dives into the fascinating world of tensors. We hope you've enjoyed the journey as much as we have.
It's been a pleasure exploring these concepts with you.
And to our listeners, keep those data explorations going, and we'll catch you on the next deep dive.